Okay, I'm recording now. Today we're going to continue to explain ventilation loads. So if you remember, I explained what ventilation loads were. I explained why we need ventilation in our buildings. Okay, so we need ventilation because we need fresh air. If this is a building, we develop an activity inside the building. We breathe, we sweat, we expel moisture and other things to the air, and then we have to get rid of it. There's a usual way to do these kind of things. We can open windows. Okay, so we need a supply, and we need to extract. Okay, so every time we are talking about ventilation, we always need a supply. And we need to extract air. Okay. And at the same time, or we can do this if we are just opening windows, we can say that this is natural ventilation. Okay. Or if we use a device to force the air supply and the air extraction, we will have mechanical ventilation. We can have a hybrid ventilation. If we have, for example, a natural supply, if we open window for air supply, and then we have an extractor that extracts air, that would be a hybrid ventilation. But we can divide ventilation into natural ventilation and mechanical ventilation. Natural ventilation by opening windows. It's important if we open two windows that are opposite to each other, because if we only open windows in one of the walls, natural ventilation won't be as effective as this, okay? But if we open these two windows in opposite walls, we will force, or we will facilitate this natural ventilation. If we don't do that, we always can have a device, and then this device will move the air from outside. We need to supply fresh air, and then we need to extract this air and get rid of it. Sometimes we can have mechanical and natural ventilation in the same building or in the same room. It depends, and sometimes mechanical is more effective than natural ventilation. But I explained that usually in single-family houses we have natural ventilation, or natural ventilation should be enough, or hybrid ventilation with natural supply through the windows and an extraction in kitchens or bathrooms, mechanical extraction. But in commercial buildings with a high occupancy, we always need a mechanical ventilation system. But we can have mechanical ventilation in houses, and we can have natural ventilation in large buildings. Okay, we explained this. This is the tool that we are going to use. This is the psychrometric chart. So the psychrometric chart relates properties, air properties, the properties that have to do with temperature, and other properties that have to do with moisture or water, okay? So all these things, the air that we are breathing, it's a mixture of different gases. So we have oxygen, nitrogen, even CO2. We need CO2 to breathe a certain amount of CO2. And we have a moisture or vapor of water. Okay, so this mixture of gases, this is what we need to breathe. But if we have an excess of humidity, or if we have an excess of vapor or moisture in the air, we don't feel comfort. Okay, so at the end, comfort, it's a question of combining temperature and humidity or water. Yeah, and there are very narrow limits in which we feel the comfort. So we feel comfort between 68 and 74 Fahrenheit temperature, and we feel comfort between 40% and 55% relative humidity. Okay, so if of all these combinations between moisture and temperature, we feel comfort only within those limits in this hatched rectangle here. So our goal when we are designing mechanical systems or we are solving building physics problems, well, the indoor air should be within those limits. 40 and 55 relative humidity, 68 and 74 Fahrenheit. So within these limits, we feel comfort. So this is the tool that we are going to use. And well, as you can see, we have 7 different parameters that we can relate in this chart. The first thing is the dry bulb temperature. We know what dry bulb temperature is. So it's the temperature that we measure, the air temperature. When we have a thermometer, we place the thermometer in the middle of the room. So this is the dry bulb temperature. The wet bulb temperature is the temperature that we measure when this bulb, when this thermometer is soaked. It doesn't mean that it's underwater. It means that it's completely covered. It's completely wet. It's covered with water. I told you that when we get out of the shower or when we get out of the swimming pool, we feel that probably the temperature that we feel is colder, or the feeling that we have it's that it's colder than people that are dry. Why? Because temperature is something objective, so we can measure that. But the feeling of warm, or I'm warm, or I'm cold, it's a feeling that depends on our body. So we feel cold when our body is losing heat, and we feel hot or we feel warm when our body is gaining heat. But it's something that depends on the people. There are people that tend to be cold, and there are other people that tend to be warm. And we can regulate that with our dress. For example, we can wear long sleeves or whatever, or short sleeves, and that's a way to regulate our body temperature. But it's not something objective. It's not something that everybody feels the same way. Well, it depends. So when we feel that something is cold, it means that we are losing energy, or we are losing heat from our body. And when we are feeling that, oh, it's too hot here, that means that we are gaining heat through our body. So that's why we have this comfort range. Okay, so within this comfort range, these temperatures, 100% of people is under comfort conditions. That someone might be more comfortable close to 74, and others might be comfortable close to 68. Okay, but below 68, everybody feels cold. Above 74, everybody feels that it's warm or too warm. So this is the dry bulb and the wet bulb temperature. So I was explaining this because the wet bulb temperature is the temperature that we feel when we are when we are covered with water, not underwater, but when our skin is wet. So the same thing we can have with a thermometer. When the bulb of the thermometer is wet, this is the wet bulb temperature. Then the dew point. The dew point temperature, well, we can explain here the definition of dew. The dew is condensed moisture. So that's the definition of dew. And this is an example. The early morning dew was in the meadow. Beautiful. Okay, so it's condensed water. So I think it's poetic if we look at the dew on a beautiful winter morning or whatever. The dew is the condensed moisture. That's what dew is. So it's very poetic, it's very romantic, it can be very beautiful, but outside the building. Inside the building, we have to prevent dew or condensation from happening, because it will damage the building. Water is an enemy. usually in buildings. So we have to get rid of water. We have to protect our building from the water outside, rain. But there's likelihood that we can have water inside the building. Of course, if we have a swimming pool or we have a bathroom, we have water inside the building. So we have to get rid of that water. We cannot keep the water for hours in our building. No, we can't do that. And the other source of water we can have in buildings, it's by condensating moisture that we have in the air. Again, we have to, it's not something that we want. So if the moisture inside the building condensates somewhere, it will cause a lot of problems, because especially materials are not, construction materials do not cope with water very well. Thermal insulation, most of the thermal insulation materials, if they get wet, they will lose their thermal insulating properties. So that's an issue. Wood doesn't work well with water at all. In other materials, with metals, we can have problems with corrosion if they are exposed to water, and even bricks or concrete or stones, they can have issues if they are exposed to water. Okay, so nothing works well with water. And the dew, it's something that can happen inside the building. If we reach temperature and relative humidity conditions inside the building, we can have this condensation. And this is not something that we want, okay? So the dew point, we need to control this in order to prevent condensation from happening. So that's why we need to understand where the dew point is, or the dew point conditions are. Then relative humidity. Relative humidity, it's a concept that we are all familiar with, but it's quite difficult to explain. So if we Google relative humidity, okay. The relative humidity, it's a way of describing how much humidity is present in the air. Okay, so how much humidity is present in the air? We all understand that. But if we go further with definitions, look at this definition. The relative humidity is defined as the ratio of the partial pressure of water vapor in the mixture to the equilibrium vapor pressure of water. What the hell is that? So it's a very complicated definition. So here we can have another definition. Is the ratio of the amount of water vapor actually present in the air to the greatest amount possible at the same temperature. Okay, so yeah, I think this is the best definition that I have found so far. Is the amount of water vapor, okay, we're talking about water vapor, moisture, actually present in the air to the greatest amount possible at the same temperature. Okay, so we are, it's relative to what? It's relative to so it's the amount of water that we have, but I have to compare this to the maximum amount of water that we can have at the same temperature, and that's important. Okay, so it's complicated. It's complicated. Anyway, we are all familiar with this concept, and we all can understand that if it's raining outside, the relative humidity will be very high because it's raining. And if we are in the desert without any rains, we have very low relative humidity. Okay, so it depends on the amount of water that we have outside. And inside buildings, we all can understand that if we are in a swimming pool, a covered swimming pool, or we are in a gym with a lot of people sweating, the relative humidity there will be higher than if we are in a library where with a few people, and people are quiet without moving, just reading. Okay, so that's the concept of relative humidity. But it's it's difficult to explain what relative humidity is. Okay, so we have this relative humidity, then we have humidity ratio. So the humidity ratio, it's the other way around. It's very easy to explain, but it's a concept that we are not familiar with. The humidity ratio, it's the amount of water that we have in a room. That's it. Okay, so we have the volume of the room, and we have 2 gallons of water. Okay, so this is it. It's 2 gallons over the total volume of the room. The thing is that we can have humidity as water vapor, liquid water, or solid water. Okay, so quantifying liquid and solid water, it's quite easy because we can measure it. Quantifying the vapor, the amount of vapor moisture, it's more difficult because we don't see that. So we need other devices to measure the vapor moisture. But the humidity ratio, it's something simple. It's the amount of water, vapor, liquid, and solid divided by the volume of the total air that we have in a room or a building or whatever, a space. But this is a concept that we don't use. We use the relative humidity. Why? Probably because we all understand from 0 to 100, it's very easy to understand. We have a scale, okay, 0 is very low, 100 it's the maximum. We all understand that. The humidity ratio, look at this, it's 0.0077, and the scale goes from 0 to 0.03. And okay, so having a humidity ratio of 0.00412, what's this? It's better if we say, okay, no, relative humidity is 35. Okay, 35, it's very low, it should be 40. But, okay, so it's easier to measure the relative humidity, but it's more difficult to explain than the humidity ratio. So that's why we're used to working with relative humidities. Then we have the specific volume. The specific volume is the weight, or it's the volume divided by the mass. Okay, so it's the volume of the air divided by the mass of water. So it's something similar to the humidity ratio, but with different units. But it's it's a relationship between the moisture, the water, and the total air that we are having here. And finally, the most interesting concept here is the concept of enthalpy. I don't know if this is the first time you have heard of enthalpy, but definition of enthalpy. Okay, so let's use the Wikipedia. It is defined as the sum of the system's internal energy. Okay, so this is it. It's the internal energy of a system. Here we are talking about what is our system here. It's the air. It can be an engine or it can be whatever. But we are studying building physics, and for us, our system is the air that we have in a room. This is our system. This is what we are working with. So this is the internal energy of the air. So that's the concept of enthalpy. We can understand that it has to do with temperature. So the higher the temperature, the more the enthalpy of the air. But it has to do with the moisture content as well. Okay, so this is more difficult to understand, but I think it's very straightforward. If the air temperature is very high, the enthalpy is high. If the air temperature is low, then the enthalpy is low. And this is the amount of energy that we have. So that's why when we are talking about heat recovery for ventilation, it has to do with the enthalpy. Okay, so if you remember when we were talking about about the heat recovery, so we are extracting the energy that this return air has, because the outdoor air is at 20 Fahrenheit, the indoor air is at 72 Fahrenheit. So we can understand that the enthalpy of this indoor air is higher than the enthalpy of the outdoor air. So we need to extract part of the energy that this air has. Okay, so that's the concept of enthalpy. So everything is related here. Temperature and humidity. And we can relate this with all these parameters: dry bulb, wet bulb, dew point, relative humidity, humidity ratio, specific volume, and enthalpy. Today we're going to use dry bulb temperature. We know, well, we have been using dry bulb temperature for a couple of weeks. We are going to use the relative humidity. And today we are going to use the wet bulb temperature to calculate the ventilation loads. Okay, so we need to know how we can get these values from this psychrometric chart, because at least today we will have to calculate the wet bulb temperature. Okay, then we have sensible heat and latent heat. So this is important as well. Sensible heat has to do with temperature. When we are changing the temperature of the air, we are changing the sensible heat. The latent heat has to do with humidity. Okay, so when we want to turn water into water vapor, we are changing we are increasing the energy, and we are changing the latent heat. Okay, so here I have this is a glass, and it's filled with water. So if you leave a glass of water on the table, you will see how, I don't know, maybe tomorrow or the day after tomorrow or in 2 or 3 days, the water has disappeared. And it's not because I have drunk or someone has been drinking water, or no, it has disappeared because the water has turned into moisture vapor. But we need energy. Okay, so that happens. But that happens because the air has a latent heat in it. And this latent heat has turned water, liquid water, into vapor. We have a limit, and the limit is when we have a relative humidity of 100. When the relative humidity is 100, we can't increase the amount of water that we have in the air. But if the temperature is not, if the relative humidity is not 100, that means that the air has the ability to turn water, liquid water, into vapor because of this latent heat that the air has. Okay. Anyway, with a sensible heat, we don't have any change in the water content. Okay, so with sensible heat, we turn on the heating system and it increases the temperature, but the amount of water doesn't change. When we are, when there are people in the room, people are breathing. They are, well, we are expelling moisture, and we are changing both the temperature and we are changing the humidity that we have in the air, in the indoor air. So this is the concept of the latent heat. Okay, so latent heat has to do with changes in humidity, the amount of water that we have in the air. Sensible heat has to do with changes in temperature. So we don't have any change in the relative humidity with sensible heat. Anyway, that is complicated, and ventilation, it's quite complicated. Okay, as architects, we don't need to study the physics of ventilation. We can, but well, we need to know that there are two kinds of heat: the sensible and latent heat. And some devices affect the sensible, some devices affect the latent heat. Okay, so this is what we need to know. Because we have to calculate ventilation loads. So in ventilation loads, we have sensible and latent loads. I explained that these two formulas, so I explained the concept of CFM. CFM stands for cubic feet per minute, and this is the amount of air that we need. And why do we need that? That depends on people. The more the people, the more fresh air we need. Okay, so the CFM is the cubic feet per minute. And per person. So we need to multiply, well, we have some guidance the ASHRAE and other regulation and building codes, they give us parameters. Okay, you need 20 CFM per person, or 15 CFM per person, or 18. Okay, and then we need to multiply this times the number of people. T2 minus T1 is indoor minus outdoor temperature, so that's quite easy. And then we have 1.1, and 1.1 is the heat capacity. So it's the ability of air to absorb heat. And it's 1.1 because it's in imperial units. It's in cubic feet per minute, Fahrenheit. So this is the value for these units. But if we are working with different units, you will have the same formula, heat capacity times ventilation airflow. So this is the airflow times temperature. But if units are not Fahrenheit and cubic feet per minute, this value would be different. So this is the sensible load. And the latent load, we have this 0.68, and 0.68 is the latent heat of evaporation, which is the amount of heat that we need to evaporate water. Okay, so to turn water, liquid water, into vapor. We can have this value for solid water, but it's very unlikely that we have solid water in buildings. I mean, I don't mean that we are drinking something on the rocks. So a couple of ice cubes, this is not solid water, because it will be, that doesn't affect the global indoor air conditions, or the indoor air conditions. But we don't have a lot of ice within the building. So that's why this is the value of the latent heat that we have when we turn water, liquid water, into vapor. And again, it's 0.68 because it's according to this CFM, to those units. And then this is the wet bulb temperature. Okay, so this is the indoor and the outdoor, or wet bulb temperatures. So that's it. Do you have to memorize those formulas? No, you don't. But you need to use these formulas to calculate ventilation loads. And this is what we are going to do here now. Okay, we are calculating, this is our building, the building we are working with. We have, let's say, 72 Fahrenheit and 50% of relative humidity inside, and 20 Fahrenheit and 70% of relative humidity. Where do we get these values from? I mean, the indoor values, everything that it's between 40 and 55 relative humidity and 68 and 74 Fahrenheit, it's fine. It can be 72 and 50, or 70 and 48, or 71 and 52, whatever. What about outdoors? Well, outdoors depends on where we are. Outdoor conditions depend on where we are. And I'm sure you can Google. Yeah, I have found this US climate data. You have a monthly, daily, so you can select month, January. And here you have the highest temperature, the lowest temperature. These are, well, here we have the amount of rainwater that we have per month, per year, the amount of snow per month, per year. And somewhere we will find the relative humidity of this. By the way, I'm working with Keene, New Hampshire. Okay, so if you open this US climate data, and here you type Keene, New Hampshire. Well, we are here in Keene, okay? You have these available, and I'm sure that somewhere in this website you can find the average relative humidity that we have on January the 1st and January the 2nd. Okay, so we have all these data available, and as long as we have an official source, that's fine. And there are plenty of these. Okay, just by clicking this, you have the, today, according to this, the relative humidity in New Hampshire is 88%. Is it raining? It's cloudy. Is it?
It is.
Okay. Yeah, so on cloudy days when it's raining, the relative humidity, it's higher. If we have a sunny day, yeah, so the relative humidity will be lower. Okay. Anyway, in New Hampshire, there are those rivers, the Connecticut River, and so the relative humidity tends to be very high. We are not in a desert, okay? So relative humidity, especially in fall, winter, we have high relative humidities. Even we have high relative humidities in summer. Anyway, you have this this data available, and you just Google that, and you can understand the temperature and relative humidity at each time. What's this? Okay. So this is something that we have to, well, depending on where we are working, we can find even we can find the temperature and the relative humidity of each hour or each minute. Okay, so it's something that we can find easily. Indoor conditions are indoor conditions, so we don't have any issue. And the occupancy, how many people we have in our rooms, it's our decision, or it's our client's decision. So imagine that this is our building. So I have decided that you have 5 plus the first figure of your ID on the 3rd floor, 10 plus the second figure of your ID on the 2nd floor. And then imagine that this is like a shop or something like that. And you have the 1st floor and the basement. In the basement, you can have like an office space or storage or whatever. So there are 3 plus the second last figure of your ID on the 1st floor, and 1 plus this on the basement. Okay, so this is, we have 3 spaces. We have this one, then we have that one, and then we have the 3rd floor. Why? Because we can analyze the building, the whole building, or we can analyze different units. And when we have multi-purpose buildings, this is what we have to do. We have different uses in the same building. And for example, educational buildings or the TDS center or all the buildings that we have in campus, they are multi-purpose buildings. We have classrooms, we have laboratories, we have offices, we can have a lobby. Okay, so there are different uses and different occupancies in different parts of the building. So it's not, when we have a large building, we don't have to analyze the building and that's it. We have to analyze space by space. In single family houses, we can analyze the whole house. We can. But in more complicated buildings, we have to go analyzing different uses and different occupancies. So this is what we are going to do here. So imagine that we have 3 different spaces, the 3rd floor, the 2nd floor, and basement and the 1st floor is the same space. The ventilation rate, let's say that it's 20 CFM per person. This ventilation rate ranges from 15 to 20. I mean, most, except we are working with a gym or a swimming pool, a covered swimming pool. In the rest of buildings, I mean, in residential buildings, in educational buildings, commercial buildings, museums, libraries, the CFM ranges from 15 to 20 per person. The more, the better. I mean, the more the CFM, the better the indoor air quality. So 20, it's better than 15. The problem is that it comes at a price, and the price is that we have to spend a lot of energy on heating up or cooling down this airflow. Okay, so I think 20 is fine. 15 can be enough, but 20 is better. So we are going to use this for all these spaces. We have 20 CFM per person. Okay, so imagine that we are working on the third floor. On the third floor, let's say that we have 5 people, sorry. Then 25 per person, 20 CFM per person times 5. So this is 100 CFM. Okay, then you have to do the same with the second floor and the basement and the first floor. But so far we have 5 people times 20 CFM per person. It is 100 CFM. And then we have to calculate the ventilation load, sensible and latent ventilation load. So the sensible, it's very easy because that equals 1.1 times CFM 100 times indoor minus outdoor temperature. So that will be 72 minus 20. That equals, so it is 1.1 times 100 times 52. So this is 5,720 units. These are heating loads. So heating loads are BTU divided by hours. Okay, so this is the sensible heat load. What is the latent heat load? So Q latent heat load equals 0.68 times CFM. It's the same, it's 100. Okay, because CFM is the same for the heating and for the latent. Times here we have to calculate the wet bulb temperature. Okay, so for the wet bulb temperature, we need to understand how this psychrometric chart works. Well, here, as you can see, we have 1, 2, 3, 4, 5, 7, and this is 1, 2, 3, 4, 5, 7. So here, if you need to know where the dry bulb temperature is, the dry bulb temperature is that scale here. Okay, so if this is 80 Fahrenheit, you can see that this line going down, it's 80 Fahrenheit. If the relative humidity is 36, relative humidity is 4. So this is 4. So this is between 30 and 40. So this is 36. Okay. And now, if we want to calculate, for example, the dew point is 50. So from this point here, if we have fixed dry bulb temperature and relative humidity, then going dew point is number 3. So going leftwards horizontally. So here we have the same scale. So this is 50. You see that the dew point temperature is 50 here. Moving horizontally towards that line, because this is 100% relative humidity. So the dew point happens, or condensation happens, when we reach to this 100% relative humidity. Okay, so this is the wet bulb temperature here. So it's this is the dew point temperature. From this point we go that way, and this is the dew point temperature, 50. Then we have the wet bulb. The wet bulb, it's 62, and it's number 2. So you see that from this point, if you go from line number 2, which is this one, you go this way, and that is the scale for the wet bulb temperature. So it's between 60 and 65. So that should be 62. Yeah, so the wet bulb temperature, it's around 62 here. And then we have the humidity ratio. We are not going to use it, but if we move through line number 5 horizontally, rightwards, so this is 0.0077. So this is here, something like this. It's close to 0.008. Okay. And then we have the enthalpy. The enthalpy, we move from this point through this line, number 7. The line for the wet bulb and the enthalpy, as you can see, is the same. It's line 2 and line 7, so it's the same. But the scale is different. So you see that this is those values here are the enthalpy values. So this is 25, this is 30. So if we are in the middle, so it should be 27. So the enthalpy, it's 27.7. Okay. Well, this is the old-fashioned way to calculate or to work with this psychrometric chart. But now technology is amazing. And I have uploaded here. Yeah. So here you have this this link. So if you copy this link on your browser, okay. We are on this website, and here we have a digital online psychrometric chart. Incredible. But here by default, you see that the temperature is in Celsius, and these are international units. We can fix it. So if we click on settings, here we can change the units. This is the metric. By default, we have the international units. We can work with the English or imperial units, okay? But here, okay, let's click here and click submit. We have this chart, which is very ugly. So we have to click here, reset all inputs here, and then submit again. Okay, so now we have a nice chart, and these temperatures are in Fahrenheit, and all units are imperial units. Okay, so by default, you copy this link, you open the website, then you have to go to setting, you have to select English units, you have to select reset all inputs, you have to submit, and then we have the chart in imperial units. And now we can start calculating things. Well, calculating, we can, yeah, we can calculate, but we don't have to make the actual calculations. We have just to take the values from this chart. So you have to click here, input data for air properties. Okay, so we have to calculate the wet bulb temperature of the indoor air. So indoor air, it's 72 and 50. Do not forget to click this, because if you don't click that, nothing will happen. But if you click here and then you click submit, there you go. Okay, so we have this green dot here at 72. This is 70, so it's 72 and 50% of relative humidity here. With the old-fashioned psychrometric chart, we would have to move in this direction, in that direction, or whatever. But here we have all the values. So the wet bulb temperature is 60. The dew point is 52. The enthalpy, it's 26. Okay. So basically, we don't have to calculate anything. We just have to click or type these two parameters, dry bulb and relative humidity, submit, and we have to copy the wet bulb temperature. So the wet bulb temperature of indoor air is 60.07. So I click here, 60.07 minus, and now I have to calculate outdoor wet bulb temperature, 20 and 70. Okay, so I open this. Outdoor temperature is 20 Fahrenheit. Relative humidity is 70. Submit again. Now the point is here, and the wet bulb temperature is 17.8. So this is 17.8. So I can calculate this. Times 100 times 0.68. Okay, so this is 2,874 BTU hour. Okay, so what is the total ventilation load? It's 5,000 plus this equals whatever. Okay, so this is the total ventilation load. Well, it's quite easy. We need to know the indoor and outdoor conditions. With indoor and outdoor conditions, we have to use these two formulas for sensible heat and for latent heat. Sensible heat is, well, we don't have to do anything, just we have to use the indoor and outdoor temperature. For latent heat, we need to calculate first the wet bulb temperature. So we can either do it with the old-fashioned, so if we fix, imagine that we have 72 and 50 Fahrenheit, then we go this way. It's not accurate because it can be 50, 55.5 or 55.6, we don't know. So that's why I prefer this one, because just by clicking here 72 and 50, submit, I get here the wet bulb temperature with 3 decimals. Impressive. Any questions about this? Hello, are you still there?
Yep.
You are there, or you have any questions?
No.
Okay, no. So you are there, but you don't have any questions. That's okay. So that's it. I mean, this is quite easy. The only thing you have to open that. Where is the link? Here. You have to open that link for the online psychrometric chart. And with this chart, you have to calculate this wet bulb temperature here. And then you have to go over the exercise we're working with, and you have to do this 3 times for the 3rd floor, the 2nd floor, and basement plus the 1st floor with different people. So you will have different answers or different values because you are working with different people here. Okay. So this is, we have to calculate these ventilation loads. And again, there will be a number, but we can improve this number, especially because as you can see, it depends on the number of people. Okay, so the difference between indoor and outdoor temperature, it's always the same, regardless of the building. We can have a mall with 10,000 people, or we can have a single family house with only 4 people living there. So the difference between indoor and outdoor temperature is going to be the same. This 1.1 is the heat capacity of air. So again, it doesn't have to do with the building itself. But this CFM, it depends on the amount of people that we have on that building. So the more the people, the more the CFM, and the more the CFM, the more the heat, the ventilation loads. In single-family houses, having a heat recovery, I mean, it helps because you can save half of ventilation loads, and little by little, month by month, you will end up saving a lot of money. But in commercial buildings, in buildings in which the occupancy is above, I don't know, 500 people, this is mandatory. So now we have to use heat recovery systems in large buildings, because all codes and all building codes, yeah, have made mandatory, because there were a lot of energy losses or ventilation loads, especially in large buildings. So we need heat recoveries. That even in single-family houses, because a heat recovery, it's not just a device that recovers heat. It controls the quality, the indoor air quality, because it has filters, so it can remove things that we don't want to breathe. Because even getting air from outside, we can have small particles. If you're allergic to something, so you need filters to prevent those small particles from entering the building. Okay, so it's not just that you recover heat. A heat recovery, it cleans up the heat, the air, and it recovers the heat that we are extracting from inside. So I think it's something that will be mandatory in the near future. And in the near future, I mean in a couple of years, especially with this pandemic, because indoor air quality, it's indispensable to control this disease. So we need to control the indoor air quality there. And we are going to need filters, clean ducts. So ventilation is going to be an issue from now. Yeah, this is what I think, that we have to invest money on a good ventilation system. Okay, so what can we do now? On Wednesday, I will explain how to calculate heating loads with a heat recovery, or how much energy we can save by using a heat recovery system in our buildings. But that will be on Monday. What do I want to explain today? Okay, so I'm going to introduce this topic, the importance of windows. Well, we have seen that windows are important when it comes to analyzing heat losses, because we are losing heat through windows. We don't have, or we can't have the same amount of thermal insulation that we have in walls, and that affects the U value. So a good U value of in a wall, it's 0.02. So let's write down these figures here. Okay, so in this, a decent U value for walls can be 0.02 units BTU over our feet square Fahrenheit. Okay, that's good. If we are talking about windows, the U value is around 0.3, let's say. Okay, so there's a difference. The U value of a window, it's at least 10 times as much as the U value of walls. So we have to be careful. We have to be careful with that. But we have something in windows that we don't have in walls. We have the ability to gain energy from the solar radiation, because windows are transparent. They are made of glass, or we can make windows, we can use plastic, but we can use a transparent material. We need a transparent material because we need natural light in buildings, and natural light is important, okay? So now we have the ability to gain heat. And this is good because in winter, we have a lot of sunny days in winter in New Hampshire. It's too cold, it's very cold, well, too cold, it's very cold. And sometimes it rains, sometimes it snows, but I think 70% of days are sunny, or we have sun throughout the day. And that's an opportunity to gain heat and to reduce the energy losses. Eventually, there will be a balance, okay? So we can gain heat, but at the same time, we are losing some energy through the window. So what's the energy we are losing through the window? It's the U value of the window times the area of the window times indoor temperature minus outdoor temperature. But at the same time, we are gaining heat. Okay, so we need to balance these two figures, the heat that we are gaining and the heat that we are losing. In New Hampshire, it's too cold, so the balance will be always negative. So we will lose more heat than we are gaining. Okay, that's fine. But if we don't open the windows or we don't have the windows well oriented, this balance will be even worse. So we have to be careful about that. And we need natural light. We need it because by having natural light, we don't need our electricity to run the artificial lighting. And this is something that we want. We need natural light because it's good for health. Okay, so being without natural light, it's not good for health. So we need it. And people like it. And probably this is the most important thing. We are architects and we are working for people. So if you ask people, okay, what do you want? Do you want a transparent facade with a lot of natural light? If you can have nice views to the forest or to a lake or whatever, or do you want to live in a bunker with a very small window here at the top just for ventilation and you want to live your whole life with artificial lights? People will say, okay, I want the first one, the first option, natural light, big windows, nice views. And that's important. So we have to balance all the heat losses that we will have with this with a good design. So we need to increase this and we need to decrease that one. Okay, so we need to reduce the heat losses and we need to increase the energy that we are gaining through the window. And we can make it, but we need to know what this is about. Okay, so it's not just, okay, which window do you want? This one. No, we have to select the glass, especially the glass, very carefully. But this is the first thing we need to understand. We need a balance. We need a balance. We have three elements here. We have the heat, because the solar radiation, we have heat and we have light. So we need the maximum amount of natural light. So that's for sure. And then what about the heat? Okay, you might say, okay, but what about in summer? In summer, if I'm in a warm country or a hot country with a very high outdoor temperature, and in addition, I have a lot of heat gains, that's bad. Yes, that's bad. So first, we need to know where are we? Are we in Florida? So do we need a lot of heat gains in winter? No, because winter is not cold there. And what about summer? No, in summer we don't want any heat gains because it's we need cooling in summer in Florida, and sometimes in winter we would need cooling as well. Okay, so where are we? Are we in New Hampshire or are we in Maine or are we in Florida or in California? So this is the first thing that we have to think about. And then we have to select the right window with that. Okay, but there are three aspects: the heat gains, through the solar radiation, visible light, we need natural or light, and we need to reduce the heat losses through the window by reducing or lowering this U value. Okay, so selecting a window, it's something that we have to think twice before selecting a window. I think this is the most important picture that you have to understand today. we have an amount of solar radiation outside. Okay, so that can be 1 or 100% is the solar radiation that goes from the sun until our window. And now from that, in that window, there are always 3 components. When we have a solar radiation, we have to think of 3 different components. We have reflection, the energy that we reflect. If we have a mirror, this is close to 100. Okay, so if we have a mirror, most of the light is reflected. We have the energy that this window or this layer will absorb. Okay, so we have reflection, we have absorption, and finally we have transmission. So if it's transparent, it will transmit part of this energy. The problem is more complicated because part of this absorbed energy will be re-radiated either indoors or outdoors. Okay, so we absorb energy. That means that we are heating up this glass, but then at night, this heat that the glass has absorbed will be either go inwards or outwards. It depends. Okay, so if we add up this component, the direct transmission because of the transparency of the glass, and this re-radiated energy that has been previously absorbed, then we have this value, what we call the G value. Okay, G. So we need to understand this. We can have a reflection, absorption, and transmission in a concrete wall. The problem of a concrete wall, well, the problem is that we don't have any transmission because it's not transparent. But we do have reflection, we reflect some energy, and we absorb some energy. And part of this energy, it's then re-radiated inside or outside. But in windows, we have this transmission component. So depending on the transparency of those windows, we have more or less transmission. We all understand that we can have tinted glasses, for example, in cars. Okay, so we know that in cars we have glasses that are almost black. So the transparency of these kind of glasses is not, so we tend to think that glass is transparent. It's not. Okay, so this glass is reflecting a lot of energy. That's what a mirror or a tinted glass is. It's reflecting a lot of energy. There are other glasses, and here we can see this. Okay, so we can transmit 30% or 20% or 5%. So we can have this light transmission. So we can control the light transmission or the heat transmission. And then by controlling the reflection, the more energy we reflect, the less energy we will transmit. Okay, so we have to take that into account. And now there's a parameter that deals with this transmission. There are 2 parameters, actually. One of them is the G value, and the other one is the solar heat gain coefficient. Okay, so if you go over glass catalogs, there will be some catalogs that we have a G value or we have a solar heat gain coefficient. What's the difference? Well, the first difference, the G value is what they use in Europe. So in Europe, if we are dealing with a glass manufacturer, they will inform about the G value. In the United States, they are dealing with the solar heat gain coefficient. So what's the difference? The G value, it's just for the glass. And the solar heat gain coefficient is the energy transmittance of a window or door as a whole. We mean glass and frame material. So I don't know. I think it's the same. I mean, there's a difference, but if you look at the window, the The frame, it's something very small compared to the area of the glass. The larger the window, the less, or the less the amount of frame that we have. Basically, we have a huge glass and we have a very narrow frame around it. So we tend to think that, okay, it's the same, okay, because most of the window is glass. So the frame matters, yes, but there's like 5% of frame and 95% of glass. So in this course, we will either mention G-value and solar heat gain coefficient. There won't be a difference between these two coefficients. Although you should know that it's different. If you are working in the United States, you are talking about the solar heat gain coefficient. It takes into account the glass and the frame. If you are working in Europe, they will inform you about the properties of the glass. Then the frame, it will be in a different catalog. Okay, so it's different. Anyway, it ranges from 0 to 1. 0, it's a window with no solar energy transmittance. Okay, so 0, it's basically it's not transparent. 1, it's 100% of transmittance. 100%, it's impossible. So in practice, most of G values range between 0.2 and 0.7. Okay, 0.7 means that 70% of the solar energy enters the building. 0.2 means that only 20% of the solar energy enters the building. So what is, because I can select, or I can decide, or first I want to decide what kind of windows or what kind of glass do I want to use, something close to 0.2 or something close to 0.7. Well, it depends on where we are. Because if we are in a cold country, I would say that the G value or the solar heat gain coefficient has to be as high as possible, close to 0.7. If we are working in a hot country, I would say that it should be 0.2 or as low as possible. Because in hot countries, basically in winter, we don't need heating because it's going to be a mild climate. In summer, I want to reduce the cooling loads. So a good way to reduce the cooling loads is to reduce the solar heat gains. So having a very low solar heat gain coefficient is good. In cold countries, in New Hampshire, I would use this kind of glasses because summer is not an issue. It might be, or you might think that summer in New Hampshire is hot, or it's unbearable. It's not, but winters are. Okay, so I would say that in cold countries I would use these kind of things. In warm countries or hot countries, I would use 0.2. There are other places with cold winters and hot summers. There are places like that. Okay, so in places like that, unfortunately, we can't change the solar heat gain coefficient of a glass. So we have to decide either a high or a low solar heat gain coefficient. So that depends on the use of the building. If you are going to use the building in winter and in summer you have holidays, so your concern is winter. If it's the other way around, if you are not using the building from November to February and you are using the building in summer, then you might think that you need low G values. It depends. Okay, but it's a very, you have to think twice before, okay, what kind of glass? Doesn't matter, this one. No, think about this. And it's not only about the U value, so we have to reduce the U value always in hot countries or cold countries. But when it comes to the solar heat gain coefficient, we have to think twice. Okay, so is it cold or is it hot? Do we use the building in summer or in winter? Is it the south window or is it a northern window? so we have to take all these things into account, because basically this balance has to be as good as possible. The balance between heat gains in winter and heat losses. Okay, then I have loaded this, or I have this chart, because when you are dealing with a glass manufacturer, you will receive this information. So I will zoom in. Okay, so you're going to receive this information. So here we have the kind of glass, HEZ, PPJ, no PPG, Guardian, whatever. Okay, so those are different brands or different glass manufacturers. Here you have the name of the product: crystal gray, solar bronze, gray, green, whatever. And this is the important thing. So here we have visible light. So here we have the transmittance, the reflectance to visible light. And here we have the solar heat gain coefficient. So the solar heat gain coefficient has to do with the heat, and then we have another parameters for the visible light. Look at this, we can have 62% of visible light transmission, or 34% of visible light transmittance. Okay, so with this one, with a 62, we have more natural light than this one with 34. Okay, so this is something that okay, are we working in a classroom? In a classroom, I think it's good having natural light. If we are working in other places, we might not need that amount of natural light. It depends. And then we have the solar heat gain coefficient. So those solar heat gain coefficients are pretty low. As you can see, it's 0.27, 0.31, 0.35, 0.2, okay? Are very low solar heat gain coefficients. So this might be a catalog for solar control glasses. So the kind of glass we can use in summer or in hot countries, because those solar heat gain coefficients are pretty low. And then we have the U value. Here we have the U value either with air or argon. Usually we have to use argon because the U value is lower. So the same glass, this is 0.29, this is 0.25. And when we are using argon, the U value is better. Okay, so this is low E. So this is a low emissivity glass. I told you that using low emissivity, it's always something good. Okay, but here we can. Okay, so this is a triple glass. So with triple glass, we reduce the U value. Okay, with the double glass, you see that we can have 0.2, 0.19, but with the triple glass with argon, it's close to 0.1. So this is much better than those. But the solar heat gain coefficient, it depends. This is 0.36, 0.39, 0.31. Yeah, I think in this catalog, all the solar heat gain coefficients are very low. Okay. So here we have other catalogs with 0.54, 0.41. So it depends. If we want a very low U value with a very high solar heat gain coefficient, we have to look for it, and we have to talk to the glass manufacturer. And yeah. But it's a question that yeah, we have to select the right glass, because we are, especially if we are committed to good architecture, and good architecture nowadays means large glass areas. then we have to select the best glass available in the market. And yeah, so we have to deal with companies. By the way, what kind of companies, of glass companies, do you know? Well, I think in the United States, the biggest glass manufacturer is Guardian. Guardian Glass. Mm-hmm. Let's see the Guardian Glass Europe. Up. Okay. Well, this is the logo, but I can't open the US website. Anyway, if you are interested in that, just Google Guardian Glass Services, and you will find a lot of information about different glasses. So glass, it's something that, again, glass, it's the same. No, there are thousands of possibilities in windows. Okay, so it's an amazing world what we can do with glass. So I think Guardian is the most important brand or glass manufacturer in the United States. In Europe, we have Saint-Gobain, which is a French manufacturer. I can open a French website. Well, okay. Anyway, Saint-Gobain is probably the most important glass manufacturer in Europe. And I think there's another one, Pilkington. Glass. Okay, this Pilkington, of course, they have brands they have in North America, South America, Middle East, Asia Pacific. So those are multinationals, multinational companies. Pilkington, I think it's from the UK. So Saint-Gobain is from France, Pilkington is from the UK, and Guardian is from the United States. But there are like 5 or 6 different glass manufacturers all over the world. Okay, so no more than this. So all the glasses that we are looking at in our houses or the buildings where we are living, if you're in the United States, 80% of the glass will come from Guardian. If you're in Europe, 80% of the glass will come from Saint-Gobain. Okay, but then there are small manufacturers. So those big manufacturers, they manufacture the glass. And then there are other manufacturers that manufacture the window itself. Okay, so it's a complicated world. Anyway, there are a lot of options, and it's our responsibility to select the right glass. So we have to deal with the right manufacturer. But it's important, believe me, especially if we are dealing with this kind of problems. Anyway. We have to go over catalogs because we can't decide or we can't calculate either the U value or the solar heat gain coefficient. So we need to find this information in this catalog. Okay, so we have information about the U value and we have the information about the solar heat gain coefficient. And this is what we need. And then we need to calculate the balance. Okay, so this is important. This ratio between heat losses and heat gains. The heat losses is the U value of the window, the area of the window, indoor minus outdoor temperature. You have already done this in that building. But then you will need to calculate the heat gains. So the heat gains depends on the solar radiation, the solar heat gain coefficient, and the area of windows. Okay, so it's pretty easy to understand. The solar radiation, it's like the outdoor temperature, it's like the relative humidity. It's something that depends on the location where we are working. So in Keene, there will be less solar radiation than in Miami because we have fewer sun hours and the days are shorter, and probably there are more cloudy days in New Hampshire than in Miami Beach. Anyway, so this is something that we have to, depends on location. The solar heat gain coefficient depends on the class, so we need to go over catalogs and we have to select the right solar heat gain coefficient. And then the area of the windows depends on us, on the architect. Okay, so we can, this is our design. So we have this balance between heat losses and heat gains. Okay, so what do you have to do? I will post an assignment now, and I will post an assignment on this. Okay, so you have to calculate the ventilation loads without the heat recovery. So imagine that there is no heat recovery. So you have to calculate the sensible heat and the latent heat just by knowing the number of people and the CFM, and you have to calculate the wet bulb temperature. Well, I have already calculated this because you will be working with these conditions. So you have to calculate your ventilation loads of this building. So you have already calculated that, the envelope. Okay, but now I want you to do this in a different way. So you will calculate the heat loads. You have already calculated the whole building heat loads, but now I want you to go floor by floor. So if we have this floor here, the third floor, so on the third floor you have to include the wall area, the window area, and the roof area. But on the second floor, you only have to include the wall and the window area because you don't have any roofs. And here you have to calculate the wall, window area, and the basement, because on this unit, we don't have a roof because the temperature here is 72 and the temperature here is 72. So we don't have any heat transmission through that floor or through that slab. Okay, so now you have to calculate the heating loads, but imagine that we have three different units. What is the height of this? So it's the total height of the building divided by 3. So this is the height of the wall. This is the roof area. So now you have to calculate, okay, what is the thermal load of the third floor? The thermal load of the third floor is the area of the walls, the area of the windows, the area of the roof. On the second floor, you have to calculate the area of the walls and the area of the windows. You don't have any roof and you don't have any floor. And the unit that it's made of the basement and the first floor, you have to calculate the area through the basement and the area through the wall and windows. Okay, so it's basically doing the same, but in a different way. We have already calculated the thermal loads of the whole building. Now we are dealing with different units. We have the third floor, the second, and the basement and the third floor. And then you have to calculate the ventilation loads of each unit. The third floor, then the second floor, and then the basement and the first floor. Okay, so now we are going to add up the thermal loads of the third floor, and we will differentiate between the envelope and the ventilation. The second floor, the envelope and the ventilation. And basement and the third and first floor, the envelope and the ventilation. Okay, so I'm going to post that assignment, and we have to do it again. I mean, by doing this like 3,000 or 4,000 of times, you will end up internalizing what we are doing here, and then you won't have to think about it. And this is the goal of this course. Okay, so we have heating loads, U value times area times difference of temperature. It takes 5 minutes. So by doing this many times, you will get to know how to do it. And then the ventilation loads, well, this is the first time you're going to do this, and we have to do it 3 times on the third floor, the second floor, and here. And on Wednesday, I will explain the energy saving measures. Okay, so if we don't do anything, we are calculating thermal loads, envelope and ventilation. That's it. Now we are designing efficient buildings, zero energy buildings, passive house buildings. So we are being more aggressive in our design when it comes to energy savings. Okay, so now we have to measure those energy savings. I will teach you how to calculate the savings using heat recovery, and we will take into account the passive solar heat gains. Okay, so at the end, we will compare a window without any improvement and the window with improvements. Okay, so this is a window that other students from other universities can design. Okay, yeah, so we have a good U value, we have ventilation, that's it. But we are calculating, or we are designing zero energy buildings, or the goal will be to design a zero energy building. So we need to improve the performance of the building. And a good way is to use the heat recovery, and we can take into account the solar heat gains. So we will have to select first the best glass available in a catalog, and yeah, we will have to subtract the energy that we are saving to the energy that we have calculated at the first time.